Now we'll consider so-called zero-force members. It can be helpful before we even start solving a problem to be able to identify what members in our truss are going to have zero force. And we're going to be able to do this by inspection for some of them before we even write down a single equation. And the benefit of knowing what has zero force in it before we start is it's going to eliminate variables down the road. If we already know the force in one of the members is zero, then there's no need to solve for it. We already know before we write down any equations or free body diagrams, that member is going to carry no force. So how can we, by inspection, identify zero force members? What we can do is go pin by pin and look at the members attached to that pin. And from that pin's perspective, we can see if that pin 1 has no external loads or supports, and then look at the members attached to the pin. Is there a member that has a direction that only that member has? And we'll see on the next slide what this looks like. But if there's a member that is the only member pointing in a specific direction, that member must be zero force. Now, this is a sufficient condition, but not necessary to be a zero force member. So we're not, with these rules, necessarily going to be able to identify every zero force member. That is to say that this is inclusive. We can say certain members are definitely zero force members, but the opposite is not true. We cannot rule out any member being zero force if it does not meet these conditions. So we can quickly go pin by pin, look at if any members are satisfying condition number 2, and say that they're a zero force member. And what we can actually do is go through multiple times. So we might eliminate one member as being zero force, in which case we can pretend it's not even in the structure, and then go through pin by pin again and see if any new zero force members are going to crop up. So as a quick demonstration, let's look at this small truss structure and see if we can identify without writing any equations, if we have a zero force member. So let's go A first. So we go pin by pin from that pin's perspective, what is happening. So at pin A, we have a roller. So if we look at our rules here for identifying certain zero force members, from the pin's perspective, that pin cannot have an external load or support. So A has an external support, so we're just going to skip over it and not consider anything attached to it from its perspective. Let's go to pin D. Pin D has an external force on it, so we're not even going to go any further to start looking at any members attached to it. Pin C, it has an external support. It's a pin, so from its perspective, we're going to move on. So pin B I saved for last because if we look at pin B, there's no support attached to it and there is no external force. So condition 1 for the pin is satisfied. So point B does not have an external force, nor does it have a support. Now we can start looking at the members attached to point B. We have AB, BC, and BD. So if we look at AB and BC, they are both horizontal. They share that horizontal direction, which we would typically call the X direction. If we look at BD though, it has its direction vertical. In fact, it has nothing along the horizontal direction, and it's the only member attached to B that has a vertical component. So this is condition number 2. One attached member lies in a direction by itself. BD is the only member attached to B that has that vertical component. Therefore, BD must be a zero force member, because thinking ahead, if we draw the pin diagram for B, when we sum forces in the y direction, the only force in the y direction has to be BD. Therefore, BD must be a zero force member. Now, how can we say BD is a zero force member? Well, it satisfied our conditions, but let's go backwards. When we were talking about point D, that external load of 450 said that we should exclude D even from consideration of zero force members. But that was not saying that we know for sure that every member attached to D was zero force. We just cannot conclusively say from the perspective of point D that we have a zero force member. So it was not until the viewpoint of B was taken into account, then we could say for sure that BD was a zero force member. Now, in a larger problem, we could go around and we could try to see on a second round if we have zero force members. We've used B, we've now eliminated BD. However, in this particular one, A, again, still does not satisfy condition 1, nor does point D, nor does point C. Going back to B, we have AB and BC, but those still share a direction, the horizontal direction. So by inspection, we can only say for certain that BD is a zero force member. So we identify one zero force member, we've eliminated one variable in this very small scale problem. So with the zero force member, we can basically eliminate it from consideration. We know it carries no load. So what's the point of having zero force members at all in our structure? Well, there's a couple of reasons. Some examples of this are, one, it provides redundancy in case of failure. So there's a certain way we think our structure is going to be loaded, but it's possible that it's overloaded. Or let's say over time there's corrosion on our truss structure and one of the members in the truss fails. At that time, something that was before a zero force member may now have to take on load if another piece of our truss has failed. So even by the intentions of the design, it was meant to carry no load. If that changes, if a member of the truss is eliminated, or maybe a force in the truss gets too high from what we expected, a formerly zero force member may now have load running through it. Probably the most important reason to have these zero force members in is that it can split long members into two members, which is going to prevent against buckling. Buckling we'll discuss in much more detail in Strength and Materials, but basically buckling is a way that a long member can fail in compression. And the way it's going to fail is going to be proportional to the square of its length. So basically the force required to buckle something is going to be proportional to 1 over L squared, where L is the length of the member. So if we're able to take one long member and cut it into two members half as long, we actually increase the force it requires to buckle it by 4. So if we're able to split it up with a 2-force member, this is a really good gain for our system. And members can only fail in buckling due to a compressive load. It's not going to fail due to a tensile load. And a third reason for zero force members is that typically in our analysis, we're not considering the weight of the members themselves when we're doing the analysis, because typically the weight of the members themselves is much, much smaller than the loads that they are supporting. So they're virtually negligible compared to those external forces. However, they do have weight to them, and if we did consider those weights when we're doing our analysis, we would find that most of the time zero force members are not actually zero force members. They are carrying a little bit of force due to the weight of the structure itself. So as we're going through this identification by inspection of zero force members, what we want to be aware of is if we actually go through the equations in the math, that is also going to reveal zero force members to us if we actually go through the equilibrium equations. So if we don't identify them ahead of time, it doesn't mean that we're not going to be able to detect them later. In fact, it's probably safest, especially as you're first learning how to do trusses, to not pre-identify things as zero force. Because if we don't identify it as zero force up front and it turns out it is, well, the math will tell us that we're right. However, if we identify something as a zero force member and it turns out that we were incorrect, it's going to throw off all of our solutions and the math is not going to be able to correct us in that event. So the worst case scenario of not identifying something as zero force is we'll have one more equation and one more unknown in our system. On the reverse, if we identify something as zero force and it's not, then our entire solution is probably going to be incorrect.